Hi guys, today we're going to be discussing covalent compounds in a little bit more detail. So first I would like to give you a summary of what we're going to be covering. The first thing that we're going to be talking about is bonding in terms of orbital overlap, and in this section specifically we're going to be talking about sigma bonds only, and pi bonds are going to be covered in the hybridization videos. The next thing that we're going to be discussing is going to be covalent compounds, and these can be classified into two types. So we're going to have simple molecular compounds and giant molecular compounds. And in this video, we're going to be talking about the properties of simple molecular compounds. And these can be further classified into two types, which is going to be polar and non-polar. And if you're confused about polar and non-polar compounds, then there's a video on that, so you can go check that out. The next thing that we're going to be discussing is going to be sigma bonds. So one sigma bond refers to a single covalent bond. And this can be further divided into three types. So we have the SS orbital overlap, the SP orbital overlap, and the PP orbital overlap. So for the first one, the example that I'm going to be using is going to be H2, which is hydrogen gas. So in this case, if you write down the electronic configuration of hydrogen, you're going to see that the valence orbital is actually an s orbital. So for H2 to be formed, two s orbitals need to overlap. So in this case, this diagram over here shows the overlap of two spherically shaped s orbitals. This is the first one, and this is the second one. And these, the ones that I've marked in yellow circles, are going to be the centers of these orbitals. And I've joined them with a green line. So this green line basically refers to the bond length. And if you mark half of this length, this is going to be called the bond radius. And another way to draw this is going to be this diagram. So in this case, this entire thing is going to be the bond length, and half of this is going to be the bond radius. So this was SS overlap. The second type is going to be SP orbital overlap. So the example that I'm going to be talking about for this is going to be HCl. I've already discussed the electronic configuration for hydrogen. So for chlorine, if you write the entire thing down, you're going to see that the valence orbital is going to be a p orbital. So for HCl to be formed, the valence orbitals for each of these are going to overlap. So the valence orbital for hydrogen is going to be s, and for chlorine is going to be p. So for HCl to be formed, the s orbital and the p orbital is going to overlap, as you can see in this diagram. So this is the s orbital, and this is the p orbital. And these are the centers for the orbitals, and you're going to join them with one line. Again, this is going to be the bond length. And half of this is going to be a radius. Again, this is another way to draw the diagram. Over here, the second one that I've drawn on the right. So in this case, this is going to be the side with chlorine, and this is going to be the side with hydrogen. I've made a partial negative charge over here, and I made a partial positive charge over here, since chlorine is going to be more electronegative. And if you're confused about electronegativity and polarity, there's another video up on that as well, so you can go check that out. The next thing that we're going to be talking about is going to be PP orbital overlap. So we're going to be discussing Cl2, the chlorine molecule. In this case, again, the electronic configuration of chlorine shows that the valence orbital is going to be the p orbital. So for two chlorines to join together to form Cl2, the two p orbitals need to overlap. So this is going to be the first p orbital, and this is going to be the second p orbital. And these two are going to overlap to give you this structure over here. And then you can join the centers, and this is going to be the bond length, like I did previously. And half of this is going to be the bond radius. And again, this is another way to draw it. So over here, if you mark this, this is going to be the bond length, and half of it will be the radius. So this was sigma bonds. The next thing that we're going to be talking about is going to be the properties of simple covalent compounds. So I have a few properties listed down over here. The first one is that they generally have low melting points and boiling points, and this is because they have weak intermolecular forces. This is mainly compared to ionic compounds, which have strong electrostatic forces of attraction. Whereas over here, the simple covalent compounds, they mainly have ID forces, which is going to be instantaneous dipole, induced dipole, PD forces, which are permanent dipole, and hydrogen bonds, which will be covered later in their respective videos. So these forces over here are going to be a lot weaker compared to the electrostatic forces that are there in ionic compounds. So this is why comparatively, covalent compounds, simple covalent compounds, have a lower melting point and boiling point compared to ionic compounds. The next point is that generally these are going to be gases, liquids, or soft waxy solids. After this, we're going to be discussing their conductivity in their natural state. So in order to conduct electricity, you need ions that are there in ionic compounds, or you can also have electrons which are there in metals. In this case, covalent compounds, simple covalent compounds, don't have either one of these. And by electrons, I mean free moving electrons, and by ions, I mean free moving ions. So both of these are not present in simple covalent compounds, and because of that, in their natural state, they're not going to be able to conduct electricity. However, they can conduct electricity in aqueous state when they're dissolved in water, as they can dissociate into their ions. So for example, we have HCl over here, and when HCl is dissolved in water, it's going to dissociate into H plus and Cl minus ions, and these ions are going to be able to conduct electricity. So in their natural state, simple covalent compounds cannot conduct electricity, but in aqueous state, they can conduct electricity. And the next thing that we're going to be talking about is solubility. So a polar molecule can dissolve in a polar molecule. For example, if we have HCl and water, HCl is going to be soluble in water because both of them are going to be polar. However, if we have water and we have oil, these are not going to dissolve because oil is non-polar and water is polar. And this is going to be discussed a little bit more in detail in the video about intermolecular forces of attraction.